did during the last 10 minutes yesterday. So I have a Riemannian surface connected at least. And I have a finite family of one forms. Holomorphic one forms. And a set of non-commuting free variables. Non-commuting but associative. So they generate for me a ring of formal series with complex coefficients. And if I have a point, a fixed point A and the variable point Z in X, I construct an expression that was denoted this way. So omega is a formal linear combination of my forms with non-commuting coefficients. And you should imagine this like as a kind of multiplicative integral from A to Z from the family of this forms. And what it actually does, so you're imagining that I have chosen a path from A to Z, and all the points here are sitting like that on this path, and I'm integrating. But since the forms are holomorphic, therefore closed, nothing depends on the path except for the homotopy class of this path with fixed ends. So if Z is in one connected neighborhood of A, then I can forget about the path. And the meaning from the viewpoint of iterated integral is that this is kind of generating series for all integrals simultaneously. So it's something like that. I am summing over all n, and then I am summing over all monomials in AVs of degree n. So I'm taking all sequences of V. V is just a finite set which doesn't have any meaning, special meaning. And here I put A, what it is convenient, I think, AV1, AVN, or vice versa, doesn't matter much. And here I will write the usual iterated integral of forms which are taken from my initial family. So you see that this is perfectly understandable expression. This is a number or a function of Z, And this function is taken as a coefficient in this formal series, and say I can write differential equations for this function, treating AV as constants. And then I have shown that the basic differential equations that is governing this series looks as follows. I could have written this, of course, term-wise, coefficient-wise. So any particular coefficient up there, if I derivate with respect to z, then just the leftmost integral is killed, and I have omega v1 and so on. So it's totally trivial, but in this way it's very nice. dj, thank you. Thank you. So coefficient-wise, it's totally trivial, but written in this way, it's very compact. It treats simultaneously all the integrals. And in addition, this is the unique solution of this differential equation in a simply connected neighborhood of A, satisfying the initial condition GAA equals to 1. Well, 1 because then only that 1 before the whole sum survives. Everything else becomes integral from A to A, and this is 0. Okay. And this is used in order to prove the first corollary, that if I change the base and start the base point and start integrating with B, then I get the same old function, but multiplied by a series with constant coefficients. And you check it by just checking that the same differential equation is valid for this, but it takes value 1 not at A, but at B. And therefore, the constant series that shows you the transition from one part to another part is this. And this should be considered as multiplicative or non-commutative version of the additivity relation. And if you look, so integral of the same story is additive with respect to paths of integration. And if you look at the linear terms in AV, of course, linear terms always encode the usual integration. If you look at the linear terms, then you will see that this is just a part of this story. But what is important here is that here we can interchange two sums, of course, because addition is commutative. But here you cannot interchange these two. You should remember that A to the left downstairs kills A to the right upstairs, but not vice versa. So you cannot interchange these two things. You are in a very non-commutative group. Okay. Now, then, you should ask the following question. Okay, there is another formula telling that if you are integrating something plus something, then you get the sum of these two things. What happens to this formula? So what happens to this formula? And it turns out that the result is very beautiful. The result is this. We can consider a diagonal map defined which maps this ring into the ring of formal series of the square, the completed tensor square of this ring with itself. Well, essentially, this means that I'm taking two families of variables of the same type as upstairs, and inside they are free, between themselves they are free, but they commute if you take terms from two different groups. That's essentially what I'm doing. And then, so this is a part of proposition which is a definition, and then the claim is that if I apply delta to the integral of this kind, so I simply replace each AV, so I didn't define it, delta of AV equals to AV tensor 1 plus 1 tensor AV. This is the definition. And the claim is that if I apply delta to this, the result will be just tensor square of delta. And I claim that this is the correct version of this additivity. It's not quite easy to motivate. And when I'm saying that something is similar to something else, it's not a theorem, but you try to motivate it for yourself by slightly just changing notation. Let's replace this first copy, let's denote them by AV, and this second copy, let's denote them by BV. So there are two different families. Yeah? Yes, thank you. So just replace the first copy of AV by AV and the second by BV. So you have two families of formal associative variables which commute in between. And when I'm applying, then delta to omega, then I'm essentially writing omega concocted out of A plus omega concocted out of B. So the sum of AV omega V, and here the sum of BV omega V. So actually what I'm doing is exactly what I have here. Here I replace by omega A, and here I replace by omega B. And the condition is that now, well, these commute in the usual sense. The coefficients A and B commute in the usual sense. And then this sum is replaced by this product. Okay. So I have found analogs of two standard properties of integration. But we have an additional bonus, namely claim 1. This identity delta G equals to J squared if you look at the coefficients now, it turns out that it encodes all integral shuffle relations simultaneously. So it's very beautiful. We had combinatorics, and now we have a very compact and nice algebra. So integral shuffle relations were shuffles corresponding to shuffles without repetitions. But of course, in the general case, in the illustrating example, I've written it for the series that produce multiple zeta values, and here it's just general. And claim 2, the same relation is equivalent, just formally equivalent to the fact that if I write logarithm of J, and I can write it formally because it starts with 1, so the usual formal series, this J minus 1 and then the usual formal series for logarithm, converges in the ring of formal series in AV. And then this statement is equivalent to the fact that this logarithm is a formal series belonging to formal series generated by commutators instead of multiplication, meaning that it is a completion, so which are embedded into this formal series as a freely algebra, completed freely algebra generated by AV is embedded into its universal enveloping algebra. So I skipped some formalities, but essentially this statement is the same as this statement. So again, these combinatorial shuffle relations are in fact telling you that the generating series is a Lie series and not just associative series. Well, when you pass two logarithms. Okay. So I have these two facts generalizing very elementary facts about usual integration. And the third one is kind of easy functoriality that I will be using. Variable change, one can prove somewhat more general variable change formula, but I will use only this one. Suppose that I have an automorphism of X. It can be even local automorphism, doesn't matter much. Such that if I apply the inverse image with respect to omegas, I will get something which sits in the linear span of omegas. So the whole space generated by omegas is in fact stable with respect to G star. So I'm assuming this. Then I, of course, define the contravariant map of J upon A's. Matrix will be the same, but transposed. And then a very easy functoriality statement says that if I start integrating, if I replace the integration path and integrate instead of A to Z, instead of it I integrate from GA to GZ, So I retain all AVs, but in each iterated integral, I'm replacing the integration path. Instead, I can integrate along the old path. But then replace all formal variables AV by the result of action of the transposed matrix. Yeah? It's the same matrix here. They are constants. They are, yeah, just some constants. And the same matrix, but actually it's transposed because it acts from the right. Sorry? This one? This. So I take the integral here, I change the integration path, and here it is the same, but then I apply to the formal variables AV the linear substitution G lower star. Yeah, but that's the same. I'm replacing, I can, of course, change omegas, but instead I'm changing a's, and the result applied to omega large will be the same. That's the point. You are, of course, right. I don't want to touch omega, but I'm changing a's. Okay. So this is the part of general formalism, and I would like to tell you that there is a much more extending and quite beautiful theory of Chen's iterated integrals, which can be done in the context of C-infinity manifolds, any forms of any dimension, and iterated integral will produce the run complex of the loop space. And there is a whole lot of interesting homotopy topology and some algebra in it, and so on. But this is a very particular case which I will only need for my lectures. This is quite an elementary part of this whole story. Now, I come to iterated modular symbols finally. And the content of what I can do and explain to you consists essentially of an application of this general formalism to the case when X is H, so upper half plane, or H completed by cusps. Omegas will be, I'll write now just formally, but they will be forms of modular type or cusp modular type. I will write the definition a little bit later. The integration will be mostly from a cusp to a cusp, or from a cusp to something in between, along the geodesic, which is not very important because of this homotopy property. So this will be the situation to which I will apply the whole story. But of course, I will try to stress upon particularities of the situation which cannot be imitated in the general case. This general formalism can be much more general than, produces results much more general than this small part of it, but this small part of it will be only a subset of what I will be telling when I'm specializing the whole story to this. Okay, so what I should do is explain what kind of forms I have in mind. And this is kind of reminder for those who know something about modular forms. If I have a function f, it will be usually an analytic function, of course, on C, then I can define the right action of actually I can put even R here, doesn't matter much, right action of the linear group upon this function of a fixed weight K. It produces from f and from gamma function that is denoted in this way. And I will use the normalization where the value of this function at z will be determinant of gamma multiplied by k divided by 2. Then you will apply the fractional linear transform to z corresponding to this matrix. And then we'll take the denominator and produce this expression. Okay. So this will be the first part. The second part, f, is a modular form of weight k for some gamma in SL, say, to z, if we have this identity. And then f is a cusp form. It's slightly more technical. So you can consider, first of all, its Fourier decomposition at infinity. Its Fourier series at infinity. So it should start with the first term. Or if there is a denominator or something like that, anyway, it will start with 1. And so there is no constant term, but also when I apply the action of elements of my group, GL, also satisfies this property. So at any, so maybe more geometrically, the meaning of this is this. When z tends to I infinity along upper half, along pure imaginary axis up there, then this function exponentially vanishes. Constant term could have produced a constant value of the limit, but I want the function to exponentially vanish. And the same should be true in appropriate coordinates when I'm going to any cusp. Then the form is cusp form. This will be the condition which will be used when, sorry, I need something more, which will be used when we will be integrating from a cusp to a cusp, for example, and we will be bothered by the problem whether our integrals converge uniformly. And so we want the forms to be cusp forms. Okay. And now the definition. This was preparation to the definition of what is a form of cusp omega v, which is differential, should be differential. What is the differential form of cusp modular type? So I will be considering omega of the form f of z, z power s minus 1 dz. If you wish, you should actually divide z by I and then normalize, but I will not do it. This is a simple thing. Such that, so if it's omega v, then I put v here and this v here, such that fvz is a modular form, maybe cusp of some weight kv with respect to the gamma, which will be common for all fv's. So this kind of forms I will be considering. And I will call SV the Manin argument of omega v. This number, SV here. Okay. So having this as in my disposal, I can define the first statement, in fact, specific for the theory of iterated modular symbols. It's this. You remember that the whole business of integration from 0 and I infinity and so on appeared in the discussion of Manin transform. We wanted to produce from a form a Dirichlet series. Now, I want just to replace the integration from 0 to infinity by iterated integration, and so I will get what I will call iterated Manin transform. So definition. So suppose that I have a finite sequence of cusp forms with respect to gamma. And then I have the sequence of one forms constructed out of it with various Manin arguments. And then the iterated Manin transform and iterated Manin transform it will be just an integral. I will, for some technical reason, not to introduce extra signs, I will integrate in reverse direction. So this is one iterated Manin transform. So it depends in our and I'm considering each such iterated Manin transform as a generalization of the respective Dirichlet series and would like to study it. But of course, Thank you. Okay, so I actually want, of course, the total Manin transform. So then I rename well, they were ordered here. There is no need to order them again. So I will have this series of forms replacing this, and series of Manin arguments, this, and forms. On forms, and then the total Manin transform is the respective integral J, but I will denote it now Tm. Omega, and omega is as above. So this is the total Manin transform, and it has hidden complex arguments there, and we are interested in considering this as an analytic function of many complex arguments. And the absolute convergence is furnished by the fact that I wanted all my forms to be cusp forms. So in particular, at this stage, I cannot accommodate the example which was coming from multiple zeta functions. There, I had Eisenstein series, and they are not cusp forms. They have singularities at cusps. And if I have time, I'll explain very briefly what can I do with this story. But up to now, I'm considering cusp forms only. And then you remember that the first result of rewriting a Dirichlet series as a Manin transform of some modular form was that we can prove functional equation in a very easy way. And it turns out that we can do the same, produce the same game here. So if I have weight of Fb equals to Kv, then we have the following theorem. Functional equation for total Manin transform. Yeah, well, I forgot to ask one more thing from my group. I told you that in order to have a functional equation, I need some nice involution in my group, which, yeah, thank you. I need some nice involution in my group, which sends the imaginary axis into itself. So I will assume that gamma is normalized by 0, minus 1, and 0. So essentially, z goes to minus 1 divided by z. And this, of course, will produce an involution on the space of my forms. I will denote it, this matrix, by Gn. This will produce an involution to put it into SL. We get an involution. So involution produces a basis corresponding to eigenvectors with values plus minus 1. So now I will assume that all gamma is general for all of them, okay? And then theorem. So if Fv consists of such vectors for Gn. For example, we can just take, I had there a list of weights. Okay, take all spaces together for all these weights, and in each such space, take a form which corresponds to this, corresponds to the eigenvector for this involution. So put V here, put V here, and then I will have epsilon F, and then we have this functional equation. And of course, this is more or less straightforward application of this formalism that was developed here. The point is, however, that since we have some function of many variables, this total Manin transform is a function of many, many variables SV. And of course, in this case, we would really like to have not one functional equation of Riemann type, but many. Basically, if the dimension of S's is just one, then of course we have a reflection. S goes to K minus S, and we are happy. But if we have only one reflection in many-dimensional space, then, for example, what kind of analytic continuation it would give for a Dirichlet series. It would tell me that I have a convergence in some cone, and then in convergence in a cone which is obtained by reflection. This will be the hyperplane with respect to which we make this reflection. But we wouldn't say anything, we wouldn't know anything about this story. So actually, in many-dimensional case, we would like to have a reflection group, say, of Weyl type, producing many functional equations. And this is a problem which is not solved in this context. There exists a small amount of papers which are constructing Dirichlet series of many variables satisfying many functional equations of Weyl type, but I do not know whether what we get here is in this class. But anyway, what we get now is the integral expression itself produces an analytic function defined in the whole S space, but we have only one functional equation. Yeah. Yeah, they are encoded in this. They are encoded in this action. Actually, it would not be necessary to do it, but this is just the form of this one. Gn star up star x upon multiplying by a matrix with coefficients plus minus ones. I put these plus minus ones into A, and that's it. Okay. So, as I said, I have integrals in this presentation. Integrals comes first, but Dirichlet series did not yet appear. So it would be interesting to see whether this total Manin transform has something to do with Dirichlet series. And then one additional thing, I told you that shuffle relations between integrals is very well encoded in the general formalism, so there are no problems about it. But from the example of multiple zeta values, we know that shuffles produced by integrals produce different relations from those that are generated by Dirichlet series. So it would be interesting to go back to look at the total Manin transform or to the special Manin transforms and to see whether there are some Dirichlet series, multiple Dirichlet series associated to them, and whether one can produce some shuffle relations related to this Dirichlet series and not the integrals. And here is something that I can produce in this direction. So multiple Dirichlet series. Okay, so let's start with the same family of forms, but now we will consider them only at integral points, and actually integral points of critical strip. As a preparation, I first will write here a formal Fourier series of this kind. Then I will multiply it by some power, integral power of z. And then I will assume that in this formal series, coefficients grow at most polynomially. And then I will produce a formal series depending on my forms and some additional arguments j. It is a rather long expression, but I will tell you what should you look at mostly. Essentially, the series of this kind will be what I will obtain if I will be integrating not from I infinity to 0, but from I infinity to a variable point z on my imaginary axis. Okay, so look first of all at the denominator, which I have already produced. So essentially in denominator, I have an increasing sequence of integers, strictly increasing sequence of integers. And here I will have some powers depending, some Dirichlet arguments which are integral and depend on parameters of my construction. So the denominator has the same structure as the denominator of a multiple zeta series. But now, numerators. Numerator is somewhat different. Well, there is one part which depends on z, and as I said, this dependence is elementary. I take essentially the largest number here, multiply it by z and by 2pi, and then take the corresponding coefficient. But the most unusual part of this series will be its dependence on these coefficients here. The point is that usually the easiest generalization of multiple zeta series would be like this. I have some usual zeta series with coefficients a n1, say 1, then another with coefficients a2 and 2, and then one more with coefficients a, k, and k. And this would be the usual ordinary multiple zeta series. But here, we do not have the same dependence on the coefficients. What we will have C V1 and 1, C V2 and 2, and so on, C V K and K. And N1 and 2 and K here are not 1 and 2 and K here, they are the differences of the consecutive n's. That's the point. So the structure, this is written not in the same notation as here. Here, N1 replaces N1, but N2 replaces N1 plus N2, and so on. And the coefficients that appear in this expression depend on the consecutive differences of what we have in the denominator. That's the most important structural part of this story. And then how these series appear in the theory of Manin transform if I will take the just single iterated integral. I will denote it here in this way. But it's not the whole Manin transform, it's iterated integral of this sequence of forms omegas. And it turns out to be a linear combination. I will abstain from writing the whole formula. You can find it in my archive paper. A linear combination with easy rational coefficients of this series up there what is changing? Well, these parameters jk, and essentially the j1 sits between 0 and m v1 minus 1. j2 sits in between 0 and m v2 minus 1 plus j1, and so on. So what is important to remember is that when we try to replace an iterated integral by a multiple Dirichlet series in this context, we get, first of all, an iterated Dirichlet series of non-standard type, where the consecutive coefficients depend on the consecutive differences instead of depending on these n's. That's one lesson. Another lesson, we have to deal with this variable z. Generally, we cannot put z formally equal to 0, because although my integrals converge absolutely everywhere, but my Dirichlet series do not. And one should be careful about this. This, of course, happens with usual zeta function as well. And so the transition to the limit z goes to 0 requires some care. And third, I cannot, yeah? Sorry? No, J is a total integral where I is just one coefficient. Yes, just one coefficient. And then I cannot put all these m's, I cannot take them arbitrary complex variables. Actually, they will be restricted to being integers in the critical strip in practically interesting cases. So somehow my total Manin transform or iterated Manin transform works for any complex, but if I want to translate it back into Dirichlet series, then I have to consider only quite a restricted amount of values of the Manin arguments. So this is approximately what happens. And then, of course, the reason why we would like to have multiple Dirichlet series, one of the reasons at least, is to look at whether we can prove shuffle relations for this kind of values based upon Dirichlet series representations instead of integral representation. And it turns out that if we restrict ourselves only by modular forms of the type that I have described, then we cannot. When we multiply two series of this kind, you see what happens. In one series, coefficients depend on the differences. And in another series, coefficients depend on the differences. And when we reshuffle them, they start to depend on the differences not between neighbors, but on the differences between those ends that generally can sit as far apart as we wish. So one interesting result is that if we want to construct a closed system of such Dirichlet series, closed with respect to shuffle relations, we should introduce more forms into the game. And it's quite interesting. It seems that we should introduce some kind of scalar product between modular forms before we can play the same games with the shuffle relations between series. And this is, again, a kind of research problem. One should test the consequences of such a decision. Yeah? J0 is, I think it's formally put equal to 0, I think, yeah. Well, you can find it in my preprint. It's just to make formulas uniform. Okay, so the problem of shuffles produces a quite interesting result. And then finally, I have already no time to write anything, just a few words. So to accommodate into this story the initial picture of multiple zeta values, as I said, I have to allow my forms to have at least logarithmic differentials at the end of integration. So I have to allow the integrals to diverge logarithmically at the ends. And here, what I mentioned briefly, regularization is necessary. To regularize such a kind of integral, we choose a uniformizing variable at the end of integration and just delete logarithmic divergence. And it turns out that this can be done in the same way as it can be done with usual integration. It can be uniformly done with iterated integration. This is already actually a part of the old Drinfeld's paper on this story. So I can write it systematically. He has written it for a particular case, but I can write it systematically. And in this way, we get regularized Manin transform, and it satisfies a sufficient amount of formal properties to play this game also with usual multiple zeta values. Thank you.